Assalamu alaikum, dear students. As you know, in mathematics, we have uh, usually to prove the results. And to prove the results, we have different techniques. For example, we can prove the results with the help of geometry. We can prove the results by constructive method. Okay, we can prove the results with the help of, say, contradictory method. And one such technique is there that's called principle of mathematical induction. That's also used to prove the results. But the results that are to be proved with the help of principle of mathematical induction, how are they? They are the results that involve n, that is the concept of natural numbers. That means if we want to prove a result and that result involves natural numbers, we prefer to use the principle of mathematical induction. So the principle of mathematical induction, whenever we want to prove any result with the help of this technique, what we have to do? We have to follow two steps simply. What are these two steps? The two steps are, we prove the result for n equal to 1. That's called the basic step. And next, we prove the result for n equal to k plus 1. Whenever the result is true for n equal to k. And this step is called the inductive step or induction step. Okay, so let's illustrate this with the help of an example in order to have a clear picture of this. For example, we want to prove that 1 square plus 2 square plus 3 square plus 4 square plus dash and dash up to n square is equal to n into n plus 1 into 2n plus 1 divided by 6. This is a general result, but we want to prove this. So how can we prove this? The first step is that we prove this for n equal to 1. So for n equal to 1, what we do, we take only the first term of the left-hand side. So the first term of the left-hand side is 1 square. 1 square is 1. And on the right-hand side, you see that if we will put here, instead of n, we will put n is equal to 1. We will be having 1 into 1 plus 1 into 2n plus 1 divided by 6. So n equal to 1 gives this term. So if you want to simplify this, this will be 1 into 2 into 3 divided by 6. So this and this goes, we are left with only 1. So you see that it is 1 is equal to 1, which is true. Yes, that's true. So if it is true, the truth of this equality, this step implies that the result is true for n equal to 1. So the basic step is proved. What's in the next step? In the next step, we first of all assume that the result is true for n equal to k. Okay, if result is true for n equal to k, it is the assumption. It's not, there is no proof in this assumption. We assume this is true. So if we assume this is true, then instead of n, we have to take k. So this will be the result. The statement will be like this: 1 square plus 2 square plus 3 square plus 4 square dash and dash up to k square. This will be equal to k into k plus 1 into 2k plus 1 divided by 6. Okay. So if it's like this, after that, in the same step, we prove the result for n equal to k plus 1 using this assumption. Okay. So what we do, in the given statement, we proceed a step ahead. Instead of n equal to k, we go one step ahead, n equal to k plus 1. So we write the statement like this: 1 square plus 2 square plus 3 square plus k square, and we put forward one step, that's k plus 1 square. From the assumption step, you know, this 1 square plus 2 square plus 3 square up to k square, that's equal to k into k plus 1 into 2k plus 1 divided by 6. This is from the assumption step. And the next term is k plus 1 whole square. we will make a cross multiplication of this and we get this step. Okay, we will take k plus 1 common. We are left with only this inside the braces. Okay, then we arranged the terms in order to resemble the result, in order to resemble this step with the given statement. So we break this term in k plus 1. So it is k plus 1 plus 1 into 2k plus 1 plus 1 divided by 6. If you will multiply these terms, this one I would like to highlight it here, from this up to this one, if we will multiply them, we will definitely get this step. Okay, so from the last step, if you will compare this with this given statement, it seems that and has been, it seems, we have not replaced, but it seems that and has been replaced by k plus 1. Here, n has been replaced by k plus 1. Here, n has been replaced by k plus 1. So what we conclude? We conclude that this result is also true for n equal to k plus 1. So this, for the k plus 1th stage, we have proved with the help of this assumption step. So we conclude that the result is true for n equal to 1 for the basic step, and the result is true in the inductive step as well. We conclude that the result is true for all natural numbers n. So if it's true for all, it's a general result. It can be used anywhere, wherever there is a concept like this. Thank you for joining the class. Thank you for being with us.